Alright, hello everyone. Today I'm solving LeetCode 98, validate binary search tree. I believe this is a pretty good problem if you're on your way to understanding trees. Pretty good to understand how to validate a binary search tree. So let's start by reading the problem statement. Given the root of a binary tree, determine if it is a valid binary search tree or BST. And a valid BST is defined as follows. The left subtree of a node contains only nodes with keys strictly less than the node's key, and a right subtree only contains node with a strictly greater than the node's key. Both left and right subtrees must also be binary trees. So if we look at the first example, this returns true because it is a binary search tree. If we look from perspective of the root value 2, if we go to the left, we see that the left-hand child is a 1, which is less than the parent's value, so this is checks off to be true. If we go to the right is a 3, which is greater than 2, so this is a valid binary search tree. If we move on to the second example, this returns false, but let's see why. From the perspective of the root value 5, we go to the left and we see that the left-hand side is less than the parent value, which is 5, so this is checks off, and this is correct. But when we go to the right-hand child has a value of 4. And 4 is less than the parent value 5. And if we look up here, the binary search tree invariant states that the right subtree nodes must contain nodes strictly greater than the key's node. 4 is not greater than 5, therefore this is false and we should return false. So, now that we understand why that is the answer, let's go about the thought process behind coding a solution like this up. Well, I like to think about it as like having an upper and lower bounds, and we're going to like essentially shrink these ranges as we go left or right in the subtree. And I'm going to go into like how that works exactly. So when we have let's pretend we don't see these two child nodes and we just have the 2 here. What determines if this node is valid? It has to be between negative infinity and positive infinity. Any natural number will be a valid node to put in a binary search tree for the first node because it's not comparing to anything. But when we go to the left-hand side, what happens? The lowest bound still stays the same at negative infinity, but the higher bounds, what's the highest possible node or highest possible value that this node can be? It's 2. And remember these ranges are non-inclusive, so it can't be equal to 2. It has to be less than the highest bounds, but greater than the lowest bounds. So is 1 in between these two ranges? It is. 1 is between negative infinity and it's less than 2. So this is valid. And we do the same thing for the right-hand side. So if we were to go right, the highest bound stays the same, so positive infinity. But the lowest bounds, you could pause the video if you like and think about what you think the answer would be. But the lowest bounds would be, again, equal to 2. And we want to know. And remember, the bounds are, just say it, reiterate that the bounds are non-inclusive. So this node's value has to be greater than the lowest bounds, i.e. greater than 2, but less than positive infinity. 3 is in between these two ranges, therefore it is valid. And we just follow that same exact algorithm as we go down, changing the highest and lowest bounds. And if it ever violates that rule, then we return false. And let's quickly go up to an example here of why this one is invalid. So we start off and we have negative infinity for the lowest bounds, positive infinity for the highest bounds. And when we go left, the negative infinity stays the same, but the highest bounds will be 5. Is 1 in between negative infinity and 5? It is, so this is valid. And when we go to the right hand side, remember the highest bounds will remain the same, so it's going to remain the same from the parent. So as you can see, it was positive infinity here, so it's going to stay here. And the lowest bounds will be 4. Or sorry, the lowest bounds will be 5, which is the parent's value here. And we're going to say, is 4 in between our two ranges? It is actually less than our lowest bounds, so that means that this violates the binary search tree invariant, and this is invalid. So at this node here, we can tell that this binary search tree is invalid, and we could just return false. So let's quickly go up and how do you actually solve this in code. So if any part of this video doesn't make sense, make sure to comment down below and I'll help you out, or text me on LinkedIn or anything like that. So first we're going to start off with a depth first search. We're going to say DFS, well first we need to define our function. So depth DFS, and we're going to need 3 things. We're going to need the current node, our lowest bounds, and our highest bounds. And in any good recursive call, we need to have a base case. So if not node, return true. Because all this says is that we get to the point where there is no more nodes, i.e. we've traversed the whole subtree, and we have not met the clause where we've ran outside that range. We want to return true because that means it is a valid binary search tree. So this is the true clause. Next, we want to take care of our false clause. And if we hit this if condition, then that means we return false because it is a invalid binary search tree. So we're going to say if node.val is less than or equal to low, because we can't have it be less than or equal to our lowest bounds, just like when we were here. This value here of 4 cannot be anything equal to 5, which is our lowest bound, or less than 5, where it would violate the binary search tree variant. So that's the first one. Or node.val is greater than or equal to our highest bounds. We want to return false. And just to quickly illustrate that again, our highest bounds here was 5. So this value here that was 1, it can't be anything equal to 5 or greater than 5. If this was a 5 here, this would be invalid because it's equal to the parent node and it has to be strictly less than. And that goes for anything greater than 5 as well. All right, so now that we have that out of the way, now that we know each recursive call, it either reaches the end of the subtree and returns true, or it hits this if condition and returns false, which means it violated the binary search tree invariant. So we want to call that on the left and right subtrees. So we're going to say left equals DFS, and we're going to call it on node.left to check the left subtree. And our lowest bounds remain the same, but our high bounds will be node.val. There we go. And we're going to do the same thing for the right subtree. DFS node.right, and our low will be node.val, and our highest bounds will remain the same, so we're just going to call that high. Next, what we want to do is return. Since we know the left and right variables will either return true or false, we're going to return left and right, because if they're both truthy, i.e. true, that means that the binary search tree is valid. But if one of these returns false, then that means we've hit a condition, or we hit a node's value that violates the binary search tree invariant, and we need to return false. Next, all that's left is to return this recursive call. So we're going to say return DFS, and we're going to call it on the root. And for the lowest bounds, when we first start, remember we had it at negative infinity, so we're going to call float negative infinity. And for the upper bounds, we'll call float infinity. And remember, these values will be changed as we go deeper and deeper into the tree. And let's actually run it and see if we get the right answer. There we go. We solved it, and it beats 100% of runtime complexity and 68% in memory. So I hope you enjoyed the video, and if you have any questions, please comment down below.